Hello, my name is Remarkably and I am going to explain some ongoing work that we have just started with Mikołaj Bojanczyk, Rafał Stefanski and Eliom Lopez. We have identified an interesting model of computation. Here we are mostly interested in these kind of functions, functions with a string input, and the output of the function could be something, and this something could be a Boolean value, which means language, or something could be an element of a field, which reminds us of those functions that are computable by weighted automata. So as you can guess, the model of computation will characterize different classes of these functions. So let me explain the model itself. This is a two-party protocol. We have Alice, we have Bob, and there is an evil adversary which splits the input string between them. There is no limitation on the size of input, and they communicate with each other to find the value of the function. And the input of the function is split between them. Also, it is worth mentioning that there is no assumption on the computational power of the parties. This is like the model of communication complexity, but this is not exactly the same, and you will see why in a moment. So here, for example, we see Alice has one initial segment of the original input, AB, and Bob has the rest of it, ABBAA, and they send each other some messages, first, second, and third. And the goal is to compute the value of the function. The number of messages in total must be constant. This is important. So this is somehow a bounded communication. In other words, the number of messages does not depend on the input length. Also, each message consists of two parts. The first part, as you can see here, is a state, which is visible to the receiver. The second part is an element of the domain, which is a black box to the receiver. I am going to say it explicitly that what a party like Alice does only depends on what she has and the state history communicated so far, the visible parts. Consequently, the state part of the message, which comes from a finite set, can only depend on the local string and the state history and nothing else. The element of the domain can be obtained in two ways. Either it's going to be an arbitrary element that is chosen by the party based on the local string and state history, or it can be obtained, this is an interesting part of the protocols, or it can be obtained by applying some predefined operation on the previous message. And of course, the second part of the previous message. Here is an example for making everything more clear. These are messages that have been communicated so far, and the next message is the tuple that you can see here, which has the first part as Q3, which the state part is Q3, and the second part is obtained by applying addition to message number 2 and itself again. So the output domain here is natural numbers, and the only operation allowed for making new elements of a domain here is addition. As you can see, the output domain has some kind of structure. I think this is good to know that the party cannot see what D2 is here. It can just refer to it in the function application, and that's it. Yeah. The semantics of our protocols is simple. The output is going to be the second part of the last message, and so one element in the domain, and one crucial assumption is called a split invariance, and it simply states that no matter how the adversary splits the input between two parties, the output of the protocol must be the same. Hence, we have this equality and also this equality and this equality, and this must hold for all pairs of splits, as you can say, as you can guess. For Boolean outputs, so these are results. For Boolean outputs, you can clearly compute all of the regular language, and this is easy to see. Just simulate the DFA and send the last state to Bob, and Bob is going to continue simulating the DFA, and the second part of his message is going to be true if and only if the last state is an accepting state. And also, for the other direction, you can do nothing more. And the proof is just using the Myhill-Neuer theorem. I am skipping the details here. For field outputs, our model captures surprisingly exactly those functions which are computable by weighted automata. The first direction of the proof is again by simulation. The second direction, however, has a sophisticated proof and also takes advantage of Felice's theorem. In unary string, we coincide exactly with functions that are computable by two-way finite transducers, which are simply two-way DFAs with outputs. Again, the first direction of the proof is easy and uses the same technique. But the second part is more complicated and is not directly related to any other of our previous proofs. Also, it uses a lemma that says that the output always has linear size with respect to the input size. For general string, again, the first part is easy, but the second part is a mystery for us. The conjecture is that, again, the model cannot express anything beyond functions computable by two-way finite transducers, but we couldn't prove it yet. And please remember that here we have binary alphabet or more. This is an ongoing research with a lot of open questions. We are experimenting with the model by changing the output domain, and we are trying to give a new machine-independent characterization of well-known classes of function. And that's it. Thank you for listening. I'm here to answer your question.